All right. In this example, we're going to do this once, and then we'll probably use technology for the rest of the time in dealing with polar coordinates, but it's really helpful to kind of get a sense. So I'm going to encourage you guys to try at least on a couple of them until you feel more comfortable graphing. All right. So example three for the notes, we want to plot, what was this equation? It's like r equals 12 cosine theta. Okay, so r is a function of theta. Uh, so how do we do this? Plotting it by hand. Well, this goes back to our pre-calc days or when we were learning how to graph very basically in whatever grade level we were when you graphed. So uh, I like to, when I'm plotting these, I tend to literally think about the unit circle. And I go around and plot unknown values. So in the first quadrant, you have pi over 6, you have pi over 4, pi over 3, pi over 2, and then you start to develop the uh, second quadrant. And so you're just going to keep going. So you get, after pi over 2, you get 2 pi over 3, 3, you get 3 pi over 4, and you get 5 pi over 6, and you get to pi. So we're going to plot those down this way and then see what the corresponding, so plug them into theta. We're going to get some exact value out, and then that will be the output then for our graph. And so just like in ordered pairs, then we'll plot the theta value and then where the length out that it corresponds to. Okay. All right. So let's go 0, pi over 6, pi over 4, pi over 3, pi over 2. And you can see why this would be considered being a little bit maybe tedious, right? 2 pi over 3, 3 pi over 4, and then 5 pi, no, 3 pi over 4, and then 5 pi over 6, and then pi. Okay. So the theta values for this are going to be 12, because cosine is 1 at best, so it's 12, and then 10.4, and 8.5, and 6, and then it gets to 0. Cosine of pi over 2 is 0, so it's an easy one to check. And -6, and then -8.5, and then -10.4, and then -12. Okay. All right. So um, this, there's a feature about polar coordinates that usually fills. So here's my completed table there. So this is some about polar coordinates that usually feels kind of awkward or a little bit maybe confusing at first. So that's something I want to make sure that we're pointing out as we go through the process. Okay. All right. So you kind of have to go in a little bit of reverse order because you need to start the direction from the thetas, but really kind of guides where you put your point. So when theta is equal to 0, kind of feels weird that I guess I should technically have these labeled backwards. It's my bad. That's probably why it was confusing. Because we talk about r and theta, but anyway. So 0, when theta is 0, we're out here at 12. Okay, and then just like up here, I have this so at pi over 6, we're at 10.4, so it's a little bit less. And then at pi over 4, it's a little bit less. Okay? And then at pi over 6, it's a little bit less. And then at pi over 2, it's down here at 0. Now at -2 pi over 6 over 3, it's at -6. And so one of the things that's awkward about this is that you're at this point, right? So this is the pi over 2 pi over 3 line that's right here. And so if you imagine extending that down, why is it negative? Well, if it was a positive 2 pi over 6, you would be in the second quadrant. But the graph actually is going to be as a circle, kind of shifted off to the right a little bit. And so it has to be negative from this point along this line. So that's why it's over here at a -6. So likewise, you're going to have if you will, a negative 3 pi over 4, and then that's going to be a -8.5. So something like that. And of course, my graph is going to be super obvious, but, and then here's a good check at pi. It says it's at, so I'm pointing in this direction. And so this is at pi. And so if I'm pointing in if my guy is facing in this direction and I'm supposed to be at this point, then I'm going to be at a negative 12 from the origin. So that's why it gets back to here. And so the graph of this, like I said, it kind of looks, if I could draw a better circle, it's a circle uh, centered at the midpoint here between the diagonals there. So at positive 6 and 0. And so that's the circle, so it's been shifted off. Uh, so it's kind of a cool little experience. The real important thing here is to recognize that when you get down to these points, why are these negative? Is to extend those lines and to plot those. And also, because with your labels, theta is the angle you're choosing, and then r is the responding, kind of like this is the x and this is the y. I had switched those. I apologize for that confusion, but I hope that was helpful. And I'll see you in the next video. Continue just a little bit more. I thought it'd be helpful to show what this looks like in GeoGebra and use it for the next couple of examples. So the first thing is this is the rectangular coordinate system. And so I don't know if you know this or not, but GeoGebra has a really nice built-in thing. So if you go over here to, if you have a little plus thing and then go over here and then look at minor major grid lines, you can switch that to polar coordinates by doing that. And it will make everything a little bit nicer. Okay, so let's create our graph here. So first of all, if you want to graph a pair of order pair in polar coordinates, it's pretty straightforward. It's r and theta. So if you have a radius of, let's say, our first point, right, was 12, and our radius or our theta was 0. So instead of hitting comma and 0, like we would in a rectangular coordinate system in GeoGebra for polar coordinates, you want to hit the semicolon and 0. And that will give us then, do you see the 0 degrees there? That's the default. So that order pair is planted. And so it's not showing up yet because we're out of zoom there. But if you look out over there, you see that there is our point A. Okay. So we could go through and put in 10.4 and pi over 6, um, or we could create or put in their function for it called f of theta if you wanted to. But let's just check to see about how we're doing them. So 8.5 and let's do 45 degrees. So you can see that you have to write that as degrees or it won't know the input there for polar. So you just gotta be careful about that. And then let's see, we have 6 and pi over 3. And then we have 0 and pi over 2. Do you see the shape being formed? And then we have, let's see, we have -6 and 2 pi over 3. If it sees that as 2 pi or not, so let me just make sure. Okay, and so let's see if that, yeah, there it is. And let's see what else we have. We have -4 point, no, 8.5. And what did we get? That was 2 pi over 4. And we had -10.4 and 5 pi over 6. Okay. All right. So I'm not going to put the last one because it'll be, let's see, does that kind of fit? So that's what we plotted by hand in the last example. And now let's plot 12 times cosine of theta. And if you want to get theta, how did I get this? Well, if you click the little button up here, it'll pop up. You can do this on your phone or on, and then you go to ABC, and then you want the Greek alphabet, and then theta will be right there. Okay. And so if you notice, aside from maybe some, there are an exact match, which is a great sign. Okay, so let's go ahead and get rid of this stuff and go ahead and just delete everything and start over. And let's look at example 4. Example 4 wanted us to graph the equation r equals 1 minus 2 sine 3 theta. You can literally just type this out, 1 minus 2 times sine of 3 I'm gonna throw in the theta there, and there is the resulting. Yeah. Now, GeoGebra does a great job of assuming you want it from 0 to 2 pi. If you don't know that 6.28 is 2 pi, it's doubling 3.14, basically. So you don't have to specifically call it out, but let's say if you did, for example, say you wanted to do 1 or 12, sorry, 12 times cosine of oh no, 12. Yeah, I thought it was 1 minus, like what's going on, times sine of 3. Um, oh, let's do it this way. Let's go t is equal to 1. So we're going to make this go from 0 to 2 pi in steps of, let's say, 0.1. No, I make it really pi. And then we're going to do 1 minus 2 sine of 3e. Why am I doing this? Because if I shut this off, you can see so we can make a slider real quick that corresponds to the angle. So 0 to pi angle 0.1. And then let's create the function. So I'm going to make an ordered pair. It can be a point. So we're going to do 1 minus 2 sine 3t. So this will be the radius being stretched out. And then I'm going to do semicolon and t. And so this will be, so if I move t along, you can see it's kind of dancing around. And you may be thinking like, well, how is that helpful? So think about that. If you look at lowercase a here, that's the curve that we plotted, right? What do you notice is happening if I animate d? So now we're counting down. So the cool thing is you can kind of see how the curve is actually traced out using this information. And so if you started, right, so when t is equal to 0, you're at the origin. And then as you progress through increasing in order of pi, or in order of theta, you can kind of see how the different layers of the flower are being traced out, which is pretty cool. Another thing you can do is if you plot it in this formation, you can actually type, if you want to see all the points together, you could type out the locus of these points. So the locus is going to be A, the thing that's generating it, moving, and the thing that's going to be generating the curve. And so, oh, of course, now I show that. That's going to be fun. Locus reading point A, T. Well, that figures. Well, it worked just a second. I don't know why it's not working now. Anyway, well, now it's doing something really cool. So, excellent. Okay. So, I don't know what's going on with that point creating locus line. Yeah, it's not that. It should be A and T. But anyway, okay. Well, it apparently doesn't like that, so I'm not sure why. But you could see that it was following along from that line there. So it's fun to play with and kind of check out that. Another thing you can do is you can put on the trace of, show the trace of that point A. And so another way to kind of get at it is if you hit play here, you'll see that it's also tracing out the point as t increases over time. And if you wanted to, you could actually get kind of clever with your scripting and color each of these lobes in different colors and stuff like that, which is also a lot of fun. So anyways, I hope that was helpful, and I'll see you in the next video. This is example 5 here. And so I wanted to show the graph real quick just to kind of have a visual in mind, which we'll come back to in just a sec. We're going to hop over and look at the symmetry ideas that bump into in this system, in this coordinate system. So let's go ahead and consider here for a second uh, our function here. For example 5, r theta is equal to 2 sine theta. Okay, so the very first situation that we were talking about is when does the symmetry we're looking for. Uh, okay, so the first one from the notes is if we replace theta by a negative theta, okay, in the graph, and um, the function is the same or unchanged, if you will, then it's symmetric about the polar axis. Okay, and so let's go ahead and try that and see what happens here. So r of negative theta is equal to 2 sine of negative theta. Now you may recall that sine is an odd function, and so we can pull that negative out. This is negative 2 sine of theta. Well, this is the original r of theta, but this is saying that r of negative theta is equal to negative r of sine theta, which is the exact definition of an odd function. So this is not symmetric about the polar axis. Okay, so no, it is not symmetric there. All right, so let's consider then the next situation. What about 2? If we replace r with negative r, okay, if we did that and it remained unsame, then it would be symmetric about the pole or the origin. Okay, and so if we do that, we're going to get negative r of theta. And what happens if we do that? Well, that we're going to test to see if that's equal to r of theta. So without writing the r of theta part there, so we have negative r is equal to 2 sine of theta, which is going to give us r, which is equal to negative 2 sine theta, which is definitely not equal to the original r of theta. So again, no. Okay. All right. So let's check the last one, the last case. So this is not symmetric about the pole or the origin. And so the last case we have to consider then is replacing theta if it goes to pi minus theta. And this is going to help us to see whether or not it is symmetric about the y-axis. Okay. All right. So let's check this out and see. So we have r of pi minus theta is equal to 2 times sine of pi minus theta. So you'll need to recall a angle subtraction or angle difference formula for sine. And so this is going to equal 2 sine pi cosine theta minus sine always keeps the same sign. So that's one way to, or one little thing to do it. And I just know signs are opposites. Sine, cosine, sine, cosine. Cosine is cosine, sine, cosine, sine, sine. Cosine pi, cosine theta. So sine of pi, this goes to 0. Cosine of pi is a negative 1. So this is going to equal to 2. A negative times a negative makes that a positive, and that should be sine of theta. I don't know. I think I was saying cosine, cosine at the time when I wrote that. Sorry. Such that is sine of theta there. And so you can see then that the negative and the negative are going to cancel each other out. And you're going to have a coefficient of 1, and that's going to be sine. So this is going to be then 2 sine theta. So replacing r with theta, my r pi minus theta is equal to r 2 sine theta, which is equal to r of theta. So this is the same, which means that it is vertically symmetric, or it's a symmetric about the y-axis. All right, I hope that that was helpful, and I'll see you in the next video.